Let me welcome you at the beginning of the new academic year. I'm happy that we are here, well, not in full attendance, but at least several of us are here. So let me welcome you. We will start by a talk which comes from ÚFAL, but don't be afraid. We will have also talks which will come from the outside during the winter term. So welcome you. I see that the titles are a bit different from the one which we had on the web, but
sorry about
the
that.
contents seems to be the same.
Yes.
So the word is yours.
Thank you. Thank you and good afternoon, everyone. It's my pleasure to be here. And actually, the content of this presentation will hopefully be soon submitted as my PhD thesis. So I would also like to use this opportunity for a heated discussion and hear your feedback afterwards. So I will be happy for any questions or comments you might have. This is the work I have done over the course of my PhD with my supervisor, Vojtěch Hudeček, who is also present here. And it concerns low resource methods for dialogue systems applications. I will get in more detail what this means soon in the presentation. So let us start. Just to outline this talk a bit, I would like to introduce some common background and introduce the tasks. And then I will talk about 3 chapters that consider my original work and propose some solutions to solve these tasks. And finally, we should conclude and hopefully have some discussion. So for the introduction, why do we even want to have something like artificial dialogue systems? For humans, for us, it's very natural to communicate with conversations and dialogues. It's a natural means of communication, and it's the most effective one. And so it makes sense to create such an interface that we can communicate also with artificial agents and perhaps solve some tasks. And when we say conversation, it can consider a lot of different concepts. But in this work, we like to focus mainly on what we call task-oriented systems. These systems are quite well defined, and they usually the goal usually is to complete some task. This task can be, for example, search for a flight, or reserve a restaurant, or a hotel, or anything you can imagine. But in general, it means solve some well-defined goal and solve the goal as soon as and as effective as possible. And again, what are the motivations? It's convenient, it's effective, and it can be also safe. Let's say in some situations, this interface can be safe, like if you drive a car, or you just don't want to focus on communicate via different interface like a keyboard or using a screen, then using a conversational interface is a great advantage. So more precisely, what are task-oriented dialogues? And on the right, we have some conversation snippet, which we can consider a part of a task-oriented dialogue. We can see a dialogue, a conversation between a user and an artificial agent, a system, and it's about booking a hotel. So we can see some values, some words in this conversation highlighted, and these corresponds to what we call slots. These are some semantic concepts we want to capture in the dialogue. And I also included some annotations, in this case, the dialogue state, which is basically the accumulation of the slots that should somehow summarize the content of and the history of the conversation in one particular step. So we can see that the user is originally interested in some hotels and propose some requirements and some constraints. And the system also communicates other and clarify more. So the state incrementally it's incrementally filled with other slots and other values, and in the end the system have a nice picture what the user wants and can like finish the task and complete the conversation. So again, to characterize task-oriented dialogues, we usually have some well-defined goal. We have some explicit or usually we have some explicit representation of dialogue state. And what is not included in the in the example, but is crucial, is usually we have some access to an external database or some knowledge base to to be able to get more information related to the conversation. In this example, for example, as soon as the system obtains all of the required slots, it can do a database search in the like booking.com website and obtain all the hotels that correspond to the requirements of the user, and then offer the user the best options. And we have some well-known data sets. For in this work, we mostly work with Multiverse 2.2 dataset, which is a collection of over 10,000 dialogues in multiple domains and focusing on finishing such tasks. One more important concept to introduce is what we call natural language understanding, or NLU. And basically the task here is to parse the sentence into some structured semantic representation. We can see an example here. This is a common way how to represent such a semantic structure. We call it dialogue acts. And we can just imagine a triple of so-called intents, slots, and values. So for this simple utterance, I would like a cheap restaurant. The annotation would be the intention of the user is to inform the system about something. And it's informing about the concept of the price, which is the slot, and the value, the instantiation of the slot, is a cheap in this case. It's common to use such annotations, such labels, when designing task-oriented dialogue systems. And we will dive a bit more into if it's needed and how to obtain such annotations. Basically, the drawback of this approach is that for each domain, you have to, and for each application, you have to design the set of slots. What slots will be used, and what slots are necessary to obtain to finish a particular task successfully. And also, once you design it, you also need to employ experts to actually obtain these annotations. And that's something we would like to address in our work. And now, for the overall architecture of a dialogue system, let's just skip to the example again. In the real world, we usually have some voice interface with the user. So it's for ASR, speech recognition, and TTS, text-to-speech generation. But we are not really interested in these parts in this work. And then the pipeline is more or less the same. We perform the NLU, that is to parse the natural language. Then we have some dialogue manager, which can be also perhaps split into dialogue state tracking and the module during the policy decisions. And then we perhaps can have some module for generating the text in natural language. Some of these components can be merged together, or even all of them merged, or all of them implemented separately. But this is like the overall conceptual pipeline when solving a task-oriented dialogue. And now, what are some disadvantages of this approach? First, that I already suggested a bit, is a narrow application domain. Such a system has to be designed for each application, for each domain specifically, and it's not straightforward how to extend it to another domain. Also, because these systems are meant to interact with the user interactively and there is a direct interaction with the user, it's crucial to have some level of interpretability. Imagine like a banking artificial agent that can transfer your money for you. You want to have a full control over the system decisions, or at least be able to interpret what's going on. And so this is crucial. But if we use like more, I would say, machine learning based systems that are perhaps able to scale better, then we lose some of the interpretability. So there is this trade-off, and it's also interesting to address this in some way. And the last point perhaps just is related to the previous one. When we want to deploy a new model, it's quite expensive. We have to analyze the new domain, design the annotations, obtain them, and test on the new domain. So it's basically the conclusion from this is it would be nice to have like a system that is able to just learn the dialogue behavior, the conversational behavior, and it's easy to apply to new domains with low resources, with not many of labels. So in this work, we want to address some of these issues. For the cost of the model deployment, we want to explore some unsupervised method for dialogue data labeling. So one way to approach this problem, at least to make it a bit more simple, is that if we have some data available and we don't know anything about the data, we can have some method that analyze it and maybe can perhaps propose the structure of slots needed in this domain, and or something similar to this. And the other approach is to actually train a model that doesn't need all these. So to be able to train model that can use perhaps some latent representations or latent structure and is able to get the structure from the data and doesn't need the annotations, the structured explicit labels. So these are our motivations. Why do we care about this area? And now let's go and introduce the first approach. This is weakly supervised NLU. So in this task, just repeating myself, we are interested to obtain the set of slots that are relevant to some domain. So if we want to solve some particular task, we need some set of slots, and we aim to have an automated method that can design this set of slots for us, and ideally also extract the slot values from the data. So one approach would be to use some out-of-the-box semantic parser that is already trained to do this in some way. We have some semantic parsing tasks like frame semantic parsing or semantic row labeling, etc. And the outputs of these parsers can be in theory used to construct or to create a dialog system. However, these tasks are usually, these parsers are very general, and they simply give us too much information. Some of the outputs of the parser are not relevant to the dialog system at all. So we would like to get rid of this redundancy. And also, since these parsers are usually trained on like open domain data and aim to be able to address like every possible situation, in quotes, every possible situation that can happen in natural communication. This also means they don't perform well enough. So they simply don't output all of the situations we might be interested in. And so our proposed solution is, okay, let's take these semantic parsers, let's take more of them and aggregate the outputs and then analyze it. So we obtain some initial pool of candidates. Let's work with it, let's filter it, and then based on the outputs, we can train our own slot tagger or semantic parser in a way. Just to illustrate this a bit more, we have a simple utterance. I'm looking for a cheap restaurant in Georgetown. And we can hypothesize this is from some restaurant reservation dialogue. And in order to be able to complete the reservation successfully, we are interested in the value cheap, which is probably a value of some slot related to price, and also in the value Georgetown, which is related to the area where the restaurant should be located in. And now we have some parsers. So for example, output of one semantic parser would be that it takes the words cheap and restaurant, and but it doesn't really take the word Georgetown. And we have some if we employ some other approach like named entity recognition, it labels the city Georgetown correctly, but name entity recognition isn't trained for tagging concepts like cheap restaurant. So to summarize, we are interested in some kind of aggregation of all these outputs, but it's not simply a union of all of these. It's also not an intersection. We need to somehow analyze it in more details. And our task again is to find slots relevant to the particular domain. I guess I explained this problematic already, and let me just introduce the design of our pipeline, our method, which is a pipeline method. So the input is some unlabeled corpus of conversations. These are simply the transcripts of some conversations of users, maybe can be two humans or users and artificial agents trying to solve some task. And then we employ a set of open domain, out-of-the-box taggers, semantic parsers or name entity recognizers, etc. And we obtain all of these outputs and use it as input to second stage of our method, which is refinement of this pool of candidates. And for this, we iterate two procedures. It's merging and selection of the candidates. If we recall this, then this example, then basically the restaurant is something that's tagged redundantly. So we doesn't really care about these values to be marked as potential slots. So in the merging and selection stage of our method, particularly in the selection procedure, we would like to get rid of such unnecessary annotations. And also it can happen that one concept can be captured multiple times as a different concept, but from the point of view of the dialogue system, it's just one. So we would like to merge these together. And after this procedure, we obtain some refined set of candidates. It's filtered. It's smaller than the initial pool, and we use it to train our own tagging model that we then can apply and evaluate. Now for the merging and selection stage, To be able to do this, we need to somehow represent each candidate. So for this, we compute word embeddings of all the slot candidates and their values. And then based on the similarity of these representations, we can potentially merge some candidates together to form a one candidate. And then we have some ranking criteria to score all of the candidates and rank them. And we select just some of the candidates that are ranking at the top. And we iterate this process a couple of times until no more candidates are selected. And then we consider the output as our set of slot candidates relevant to this particular domain for a dialog system. And once we have this final set of candidates, we can use the initial corpus to label with these obtained labels and train our own tagging model that now should only focus on the relevant slots obtained by the merging and selection stage. In our experiments, we found that the main problem is the recall of such a method. As I mentioned, this is a problem already at the input, as a lot of these open domain taggers just don't label all of the concepts needed, and therefore we are missing a lot of annotations even after this merging and selection procedure. So in order to improve this, we introduce some threshold, and we actually modify the inference stage of our tagging model. After passing the inputs to the tagging model, we look at the label probabilities, and if some probability is high enough, then we consider the label to be there. In other words, even if the tagging model would consider with the highest probability that there is no slot at in the particular place, we can still mark it as a slot if the probability is high enough. And this proved to improve our recall and the overall performance of our method. This is like a general concept. So any kind of tagging architecture can be used in theory, but for our experiments, we use LSTM-based sequence tagging model. Now, for some of the results, to compare, we have also supervised labeling approaches in gray. Then we have our method with not using the tagger, but just using the slot of refined candidates in blue. Full method that I just introduced in orange, and green is some related work which we compare to. They basically just do the first phase of this analysis and selection process, and don't train their own tagging models. We compare on several data sets, and we can observe a couple of things. First, it helps to use the tagging model. Even with our selection procedure, we can still improve the performance if we train the standalone tagger and increase the recall the way I introduced. We obviously don't beat the supervised performance, which is expected, but it suggests that we can uncover some interesting properties and relevant slot candidates in the data. And to actually verify this, we also use the output of our method on a downstream task. So in this experiment, we use a dialog model, task-oriented dialog model, and the full version of this model is in the first row. And in this version, the model has all the labels available during the training stage. However, the authors of this work also proposed like a semi-supervised training of their model, in which they just use a portion of the training set and use the rest as unsupervised, just unsupervised data without labels. So if we use their approach with no supervision, we have this performance in the second row. And if we use our labels as the supervision for their model, we actually improve the performance of tracking the slots in the dialog. So this suggests that although our labels are arguably still noisy, they can bring some relevant information for the dialog models to be trained on, or perhaps at least obtain some interesting properties from the data. So to conclude this part, we proposed a way of using a domain agnostic tagging model. It's domain agnostic because it uses open domain taggers as input, input data label. And the output of this model is a standalone component. So although we use the third-party out-of-the-box models for training, in the end, we train our own tagging model, which essentially means this component can be plugged and used in a dialog system or as a data analysis tool without the additional dependency of these out-of-the-box model that we used for training. Yes, the experiments I just introduced. So maybe let's just move to the next part. And in this section of the talk, we will move our focus slightly, and we will talk about actually modeling the dialog. So not just doing the analysis of the data or trying to do automatic labeling, but actually model the dialog processes. And the first model I introduce uses latent actions to represent the points in the dialog, and can have some interesting properties. I would like to also point out, if you have some questions right away, perhaps you can ask, but I hope to have some discussions in the end. If no immediate questions, let me continue. And for this model, I would just like to briefly introduce some of the perhaps well-known, perhaps not so well-known models that are necessary to understand our proposed model. And one of them is variational autoencoder, or VAE. The motivation for VAE is to create robust and in a way better representations of some data. So in this picture, we have a typical autoencoder model on the left, and on the right, we have variational autoencoder. And just to recall, the task of autoencoder is simply to encode some input data, create some latent representation of the data that can be used in the second part of the autoencoder model to decode and reconstruct the data again. And typically, these models are trained with reconstruction loss. So you just essentially measure the difference between the input and the reconstructed outputs. And your aim is to reconstruct the outputs accurately. The problem of this approach is that although it can work well, there is no guarantee that similar data will be encoded the same way. So in terms of natural language, even if we have two very similar sentences with the same meaning and perhaps just one word is different, there is no real guarantee that in the latent space, these Z here, their representations will be close to each other. And we would like to have this property for a couple of reasons. One is we can interpolate between the latent representations and somehow inspect the latent space and obtain some insights and explain some of the behaviors of the models. And also, if the similar sentences are encoded with similar representations, this means this essentially makes the task of the model that can use these representations easier. Because if we already have good representations in the input, then it's easier to train some model that uses these. So to address this issue, we can use some work proposed using these variational autoencoders, which have one important difference between the vanilla compared to the vanilla autoencoders, and that is they don't really encode the data directly into the latent representation. They rather include just the parameters of a distribution. So we can assume that the data are distributed, for example, with Gaussian distribution, with some mean and variance. And the task of the encoder is just to estimate these parameters of the distribution. Basically, this means that we can also sample from this distribution during the training, and the model is forced to learn the representations in the way I described. So if two input data are similar, hopefully the model will learn to represent them with similar space, in the same space in the latent space. And not just hopefully, we actually use the training objectives to achieve this. And these models are widely used mostly in the vision, computer vision field, but also in natural language processing. And one step how to use these VAE models is called variational recurrent neural network. And that essentially combines the VAE model and the recurrent networks. And you can just imagine having a VAE at every step of the network, but the distributions that are estimated for the modeling the latent variables are also dependent on the hidden state of the network. So this means in every step of the network, we have some different assumptions and different conditions, and the VAE behaves differently. And perhaps we can see that this is a good application for the dialogue task. If we imagine every conversational exchange of user and system user utterance and system response as one step of the network, we can estimate the representations of these steps in the dialogue using the VAE. But as the dialogue state changes, because every exchange will change the state of the dialogue, this will be again encoded in the next step of the underlying recurrent network. So the next time we estimate a distribution of the lighting space, we will have different prior distribution for this. So in other words, this take into account the time dimension and the history of the conversation. So we propose to apply these models to model a dialogue in an unsupervised way. And also one crucial point to mention here is usually variational autoencoders use continuous latent variables. It can be a Gaussian distribution, as I suggested, but there are also works that can discretize and make the variables discrete using some other distributions like Gumbel. And this essentially means that these latent variables Z sampled from the estimated distributions are just one-hot vectors. And we want to explore if these land or how well these latent representations can correspond to the states in the dialogue and to the actions the system is taking. So our proposed model is based on this variational recurrent neural network. And we actually do our more modification. And that is, we use 2 autoencoders in each step, or we call it sometimes dialogue turn, which is one conversational exchange. And we separate the encoding of the user utterance and of the system utterance. Now we have basically 2 latent spaces, one for the user and one for the system. So if we want to interpret the behavior, it's easier because we essentially separated the system behavior and the encoding of the user, of the information gathered from the user. And we also use these discrete variables. And this is just to be able to interpret the representations more easily. Now, since we aim to model task-oriented dialogues, there is one point missing, and I mentioned in the beginning, and this is the interaction with with external interfaces. So imagine this simple exchange. User asks for a moderately priced restaurant serving Italian food, and the system answers with some suggestion of a place called Pizza Express. However, for the system to be able to suggest this restaurant, it needs to access some external database or a source of knowledge to be included in this conversation. And usually in the supervised approach, we just have annotations for every conversational exchange like this. So we would first analyze the user utterance and get all these slots values and construct some query to the database based on this, obtain the results, and then we can include the results to condition the system response on these results. However, in our case, we essentially just have an end-to-end text-to-text model, but we still want to be able to access this information somehow. So what we did is that we modified the training data, and this conversational exchange illustrated here is actually split into 2 turns in our data. And so the correct system response for the user question is not giving the response directly, but actually indicate I need some external information with this encoding we proposed. And if we have this kind of if we have this kind of system response, we know that we have to run some search in our database and include the results, and we simply inject them as the user utterance in the next turn. So now the system should have all the information available and can actually generate the response. Yes, and then the conversation can continue. So one way to see this is the system decide if it wants to respond or perform some external action. And so now for the results, we compared our model, which is depicted here with TOVRNN, standing for task-oriented variational recurrent neural network model, and evaluated on several data sets and compared with some baselines. So all these models are also text-based and just trained from the same exactly from the same training data. This HRET model also uses variational autoencoders, but doesn't separate the system and user responses, and the system and user parts of the dialogue. And we can see that on most of the evaluated metrics, we outperform these baseline systems. However, again, if we compare to supervised performance on these data sets, we are not getting close, but we can see that our proposed modifications have some positive impact on the model performance as measured with these metrics. Maybe just comment on the metrics. It's a blue score, perplexity, mutual information, which is measured only for the models that use the latent variables, and is a mutual information contained between our latent representations and the system responses, and also EMR, which is for entity measure rate, and it measures if the entities captured in the dialogues, such as Pizza Express, are presented, are captured correctly. And the performance is not all we are interested in with this architecture. Another interesting aspect is to interpreting these latent variables. As I mentioned, on purpose, we discretize our representations. So we essentially got these multi-hot vectors as the latent representations in our model. And we simply ask the question, does these correspond to the actions that the system will take? And how well can we predict, based on these representations, what action the system will take? And for this, we trained a decision tree classifier model. The motivation for this is that decision tree classifier is very easy to interpret. We can draw a plot like this, seeing all the decision nodes in the model, and interpret what behavior corresponds to what parts of the latent vector. And also, the decision tree classifier can perform well, but it's not very complex. So if it performs reasonably well, it suggests that the representations contain some useful information. So apart from inspecting the latent space in this way, looking at the visualization of the land models, we also evaluate the performance of predicting the system action from our representations using using the decision tree model. And although we didn't get like a 100% accuracy, we can see that firstly, there is definitely some useful information contained, because we get reasonable accuracies, I would say, with predicting the system action. And also, compared to representations extracted from other models, our approach performs the best. So this compares the decision tree classifier trained on different latent representations from different models, and our approach proved to be best in this comparison. So this concludes my second part of this talk. And now for the last one, it's about using large language models to actually model this task-oriented dialogue in an unsupervised way. Maybe let me comment right in the start. It's questionable how much this is unsupervised, especially with some models which we are all well aware of, like GPT, ChatGPT. It's not really clear what data were used to train these models. So it's quite possible that these models have seen some of the data we use. So although we don't introduce the data in training, it's possible that the models already saw that. So it's not perhaps not truly unsupervised, or we cannot be sure. But we also evaluate on a lot of open source models in which we know exactly what data were used. And in this case, we know that the models didn't see the data. So let me say what this is not. We didn't do any LLM fine-tuning. So we didn't run any further training of these models. We just used them and were interested how well will they perform with just in-context learning approach. So basically, we just design a prompt in a specific way. I will talk about shortly, and we are interested in the performance using this approach. So let me introduce our pipeline. To be able to model the task-oriented dialogue, we already know that we need to track some entities or slots, and we also need to be able to access some external information. So maybe let me this time start from the bottom and explain the last two steps. This is actually an approach that is quite common in the research community in the area of task-oriented dialogue systems. Because using language models is so powerful, people just tried using pre-trained language models to model task-oriented dialogue. But again, there is this issue with the database I already introduced. And for this, there is this trick that we divide the generation of the final response into two stages. And in the first stage, we just let the model generate what it believes is the dialogue state, so-called belief state, which is an explicit representation of the slots and values at some particular time step in the dialogue. And these can be passed and used to query the external database. And once we obtain the results from the database, we can include them in the input for the model in the next stage and generate the final response. So this is very similar to the pipeline approach I introduced in the beginning, but in this case, that is the very same model doing these two steps. And yeah, so that's perhaps the main difference. And now how we construct the prompt, we actually evaluated two variants of this approach, and that is few shot and zero shot prompts. And what does it mean in our context? For zero shot, we just construct a prompt, just giving instructions to the model how to approach the particular task. Then we introduce to the model the dialog history and the user utterance in the previous user utterance, and let the model predict the next response in 2 stages. Or we also have a few shot variant, and in this case we actually use some examples of similar conversations and include them in the prompt. So this is technique that is widely used when prompting language models, and for that we use some database which we call context store, and it contains snippets of conversations from our training data. So this actually uses some part of the training data, but we just use tens of examples, very small portion of the training data to retrieve these examples. And then, given the dialog's context and the previous utterance, based on embedding similarity, we can retrieve examples and include them in the prompt to guide the model better. And we evaluate on several models. One of them was ChatGPT. These experiments were conducted in March, so it's a 0301 version that was available back then. Also, we have a TK instruct, Alpaca, which is an instruction tuned version of the Llama model, and also GPT Neo. And again, except for ChatGPT, we have much better, we have much more information about the other models. So we can actually consider these models truly unsupervised when solving this task. Yeah, I think I already described our approach. Let me just give you an example of a prompt. So the prompt is constructed from several parts. And first is a task definition. So let's say we are talking about the hotel reservation. So we give some initial instructions to give context of the task to the model. And we also include some definitions of the slots. So in this case, we already assume we have the slots defined. We don't have the labels for them, but we know what slots, what semantic concepts we are interested in. And we use some simple instructions to include these in the model. Then we also include in the prompt. And then we also include the dialog history and the previous user utterance. This specific prompt shown here is zero shot because it doesn't contain any examples of conversations from our context store. And this is used in the first step here for the state tracking prediction. Now, I mentioned we include some domain descriptions. These are depicted in green in this example. And how do we obtain them? We actually employed one additional step in our pipeline that was used to identify the domain. So we first actually asked the model to identify the domain given a list of available domains. And then based on this decision, we can include the domain description in this way, giving each slot and the description what kind of information this slot should capture. We can also see the performance of this domain detection accuracy for two data sets, multiples in blue and schema guided data set in orange. Although we see that the domain detection accuracy differs between the models, we actually observed that it's not crucial to detect the domain very accurately each time. We did some experiments when we used an Oracle domain, so the model has always the correct domain available, and the final performance wasn't different significantly. So this actually seems like a maybe quite a redundant step to actually detect a domain. It seems that it's more important to include some examples, but it doesn't necessarily has to be the most relevant ones. Now, just how we represent our database is a simple list of entries containing the entities for each necessary to solve task in each domain. This can be a list of hotels, restaurants, etc. And in order to retrieve the information from the database successfully, we need to specify all the keys exactly and explicitly. This essentially means that when the model does this state prediction, it has to be precise. It has to have some defined structure in order to be able to perform the query accurately and successfully. And one more note here: we don't include all the database information retrieved, like in this case. We just include the number of results we retrieved from the database, and this is also approach used widely by the researchers, and it just informs the model if there is no match, you have to ask for a different venue. If there are some matches, perhaps you can give some options, etc. And the exact options can be included in the final response in a post-processing step. So the model is just informed of the number of matches available in the database. I think I already described this approach of two-stage decoding and also the motivation. So just to recall in this schematic way, when we first construct the state tracking prompt, we inject it to the model, and the model should predict some structured parsable representation of the dialog state. And once we have it, we can perform a query to the database and include the results and also the predicted state in the prompt, and ask the model again and let it generate the final response. Now let me just share some of the results. First, for the zero shot, we can see that the results are far from being accurate. We also evaluate two scenarios in each case. So in one, we let the model actually predict the belief state, and in another one we use Oracle belief state. So the model has every time it has access to the ground truth annotations of the belief state. So all the labels and all the database results are included based on the data annotation. So we can clearly see that when giving these Oracle belief state, all of the models perform better, but it's still not very satisfactory performance. If we look at the results of the few shot, it's better. Sorry, I don't have a comparison with the supervised approaches here. I have it in the paper, but I think the supervised performance for the dialogue success state of the art now is around 0.80. So it lacks, even the best model still lags behind the performance of the supervised models, but it's getting reasonably close given that these are multi-domain data, and also each dialogue can contain multiple interactions and multiple tasks. One thing to note here is that what is maybe a bottleneck or one of the issues is the actual prediction of the belief state. So we can see that even the best model, which was ChatGPT in our case, has only 0.5 slot F1, which is still very, very low for this task. And we see that if we supply the Oracle belief state based on the data annotations, the performance increases a lot. This can perhaps be addressed with some fine-tuning that can help the model to understand the task better, and also to give proper structure to the outputs, because as I mentioned, we kind of expect these outputs of state predictions to have a certain structure, and if this structure is not followed, I mean, we try to parse it in a robust way, but we have still a number of failing cases because the generated structure wasn't correct. So we assume that if we employ fine-tuning, we improve this stage, but we haven't done that in this work. And also another observation is, if we use examples, it helps. So we can see the performance of the models with respect to the success rate, so how many of the dialogues were actually successful. And on the x-axis, we see the number of examples we used. So if we use 0 examples, it's essentially a zero-shot prompting. The model doesn't see any examples that could guide it. And if we introduce some examples, we can see consistently over all of the models the increase in the performance. But if we include more and more examples that can be contained in the prompt, this doesn't seem to help much. For some models, it can even degrade the performance a bit. So I would say the conclusion, the observation from this: examples help, but you don't need a lot of them. And we also conducted some human evaluation to have some more insights into the results, and perhaps more fine-grained evaluation. We asked the annotators to not only evaluate on the dialogue level, which is the performance I was talking about until now, but also for each sub-dialogue. So if we have a complex dialogue in which the user first asks about the hotel reservation, and then it remembers they also want to have a dinner and also want to reserve a restaurant and perhaps order a taxi to commute between the two places, the model has a lot of possibilities to fail. And if it fails, the dialogue is just unsuccessful. But we ask the annotators to annotate each subpart of these dialogues. So in this example, it would be for hotels, for restaurants, and for the taxi. So even if the model can fail with the taxi reservation, for example, it would still get successful sub-dialogue for the hotel because it was able to reserve the place in the hotel successfully. This isn't like an official evaluation measure, but can provide more insights into what is happening and how the conversations are ongoing. And we also ask the annotators to measure the number of cases in which they have to clarify some information. And yes, so we can see that we got almost 80 or over 80% for ChatGPT of the successful sub-dialogues, and also the number of successful dialogues was quite high, and we didn't even need a lot of clarifications. And for the TK Instruct, which was another model we evaluated in this way, the performance was lower, but the model was actually able to clarify some of the situations. So this is frequently not the case when evaluating on these data and using fine-tuned models, because the models are just trained to the trajectories they saw in the training data. And once we encounter some problems, the models are usually not able to correct these mistakes. But with these models, it seems that we have some clarifications and we can still achieve a successful end of the dialogue in the end. And one more thing to note here is the overall numbers are actually better than what we obtained from the automatic evaluation, which suggests that the models might have some reserves in the overall performance, but they are good in communication with the humans and can understand the context of the conversation well. Yeah, so let me just conclude briefly. Perhaps the biggest issue that would improve the overall performance of this pipeline would be the belief state tracking, which could be addressed perhaps with some fine-tuning or some different representation of the structure. Actually, there are some works using, for example, SQL queries directly. So we redefine the task and not using like an explicit representation, but generating an SQL query which we perform directly. Perhaps it can work better with these models. If provided with the correct belief state, however, they can offer quite satisfactory performance, and it definitely helps to include some examples in the prompt. Now this almost concludes my talk. Let me just summarize a few final points in the overall conclusion. Definitely, modeling task-oriented dialogues in an unsupervised way is challenging. One of the challenges is to be able to connect your models with external interfaces, because they are designed in some ways. And if you don't want to include this design as a form of supervision to your models, it's hard to address this issue somehow. Also, since we are interested in controllability and interpretability of these models, it's hard to train them for to have both good performance and good interpretability. However, there are some use cases that perhaps can be of a benefit. And one of these are unsupervised way to discover the annotations. Our method that I proposed in the first part could be used for some automatic analysis, and is just actually not limited to the way we obtain the input input set of candidates. So if we now with large language models have better ways to obtain the initial set of candidates, our method could still be used to analyze this and get some insights of our data. Then it's perhaps interesting to look at the latent variable models that promise a good level of interpretability. And obviously, large language models promise a lot to improve the user experience, but although it might seem from the overall excitement, they are still not quite ready to be deployed like out of the box for some of the at least for some of the task-oriented applications because of the issues I mentioned, basically. But yeah, this will probably be changing a lot over the next months and years. So that's it from me. Thanks for your attention, and please, if you have some questions, I will be happy to answer.